One prediction number can look precise while hiding risk. LightGBM Quantile Regression gives you upper and lower ranges the model can act on. This is the setup you'll be able to run after this, which trains quantile bounds and forecasts interval bands for new demand. I'm Professor Pi, teaching AI foundations with simple Python. Many teams forecast demand with a single point estimate and then get blindsided when reality lands far above it. LightGBM Quantile Regression solves that by predicting conditional quantiles instead of just an average. That gives you a lower bound, a central forecast, and an upper bound you can use for stalking, safety stock, or alerting. It scales to tens of thousands of rows easily and runs fast enough for daily retrains in many teams. At the core, we want to capture uncertainty in a simple, actionable way. Think of quantile regression as asking, given these features, what value sits at the xth percentile of outcomes? Ask for the 10th percentile and you get a conservative low. Ask for the 90th and you get a protective high. Wider bands buy more coverage but cost more inventory or capital. We will build a small toy pipeline that simulates retail demand, fits a median model, learns a lower and upper quantile, reweights for promotions, and assembles interval diagnostics. This shows how a single average hides tail risk, and how quantile models open a safety margin that your operations can use. Quick note: this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. First, let's simulate a noisy retail series so we can see how a single average misses the tails. This snippet highlights how the demand distribution stretches beyond a single average. A NumPy random generator seeds reproducible temperature, promotion, and demand arrays that resemble a noisy retail series. Those arrays are wrapped into a tidy pandas data frame so that the demand column can be queried with descriptive statistics. Subtracting the mean from the 90th percentile captures how far the right tail sits from the naive point forecast. The printed tail gap value shows the magnitude of underestimation you would face by relying on a lone point prediction. By inspecting simple summaries, you immediately see why intervals matter for operational planning. With the tail gap visible, we now fit LightGBM to the conditional median, so we have a robust point forecast. This example trains LightGBM to estimate the conditional median via quantile loss. We use train test split, which holds back a quarter of the engineered observations, so we can assess generalization on unseen demand. LGBMRegressor, which fits gradient-boosted trees, is configured with objective equal to quantile and alpha equal to 0.5 to fit the median path, while random state stabilizes the leaf-wise boosting sequence. Predicting on the test fold gives the median series, and because alpha equals 0.5, the reported pinball loss collapses to half the mean absolute error. Increasing N estimators would typically shave the loss at the cost of extra runtime. The printed median pinball score shows how closely LightGBM's median forecast follows held-out demand compared with the naive mean. Now we want more than the median. We need explicit lower and upper forecasts to form an interval. This code pushes LightGBM beyond a single quantile by learning paired lower and upper bounds. A compact loop instantiates two LGBM regressor models that share hyperparameters, but swap alpha to target the 10th and 90th percentiles. Each model reuses the training fold, producing holdout predictions that map the extremes of the demand distribution. Subtracting the lower array from the upper one reveals interval widths, and spreading the alphas farther apart would widen these bands, while narrower gaps tighten them. The printed average interval width value tells you the typical spread between the LightGBM lower and upper quantile forecasts. Tracking widths across dates helps you see where uncertainty concentrates. Promotions are special. Underestimating during a promotion is costly, so we bias the model towards safety in those cases. This snippet re-weights LightGBM's upper quantile fit to guard against costly promotional underestimates. NumPy builds sample weight values that emphasize rows where the promo indicator equals 1, reflecting asymmetric risk tolerance. LGBMRegressor, with alpha equal to 0.9, refits under those weights, so boosted trees devote more splits to promotion-heavy regions. Pushing the weight multiplier higher would exaggerate this focus, whereas lowering it would revert toward the unweighted interval. Predicting on the holdout fold yields tuned pred, which is contrasted against the earlier bounds at the 90th percentile to isolate the uplift. The printed promo uplift figure quantifies how much extra headroom the weighted model grants promotional cases. Finally, we need a practical output that teams can use to measure coverage and decide on buffer sizes. This example assembles the LightGBM quantile forecasts into a practical interval report. A pandas data frame stacks the lower bound from bounds, the median from Q50 pred, the weighted upper bound, and the actual outcomes for direct comparison. Element-wise comparisons count how often realized demand sits inside the interval, producing an intuitive coverage rate diagnostic. Averaging the span between upper and lower surfaces, the width trade-off. Pulling the alphas closer to 0.5 would tighten the bands, but usually reduce coverage, whereas pushing them farther apart does the opposite. The printed coverage rate and AVG width values show whether the interval meets your tolerance for risk-aware forecasting. In a real deployment, you would replace the toy features with your sales history, price, inventory, and calendar flags and run the same quantile pairs daily. You would also log coverage over rolling windows and alert when coverage drifts below target, so models can be retrained or features reviewed. Recap: LightGBM Quantile Regression predicts percentiles, not just a single average. Use it when you need actionable upper and lower bounds for planning or risk control. Caveat: wider intervals improve coverage, but increase operational cost and must be tuned to your tolerance. Next step, run a small grid search over the alpha pair spacing and the promotion weight multiplier to find the best coverage versus width trade-off for your business. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.